How's it going, guys? I'm Michael Hyde, and today we're going to be going over Lab 5 Complex Spring. And it is spring. We are getting out of school soon. So, the little spring decor, if you guys caught that, is a little hint to enjoy the break coming up. Now, the experiment we're going to be going over in terms of springs is we will see an initial force launching a spring in circular motion. As we can see by this little graph on the side, this is the picture of the experiment, which we will get into shortly. Now, notice that only lasting forces after the initial force are gravity and the force from the spring on the end of the spring. And we're going to discuss how this affects longevity of oscillation, otherwise known as the period, and how this is different in a different real world scenario. Now, my little own expectation was for this to be a more extreme interaction between a non constant force and a constant force than Lab 4's oscillation of a spring and pendulum. Now, things to know before we get into this experiment are what are these non constant versus constant forces that I'm discussing? Now, the first is a non-constant force, which is spring restoration. It's a restorative force, non-constant, and proportional to the force that is being enacted in the opposite direction from this force. Now, we see here the derivation real quick, where we take the integral of force times distance, and we find 1/2 ks squared for this non-constant force. Now, the other force acting upon this system is gravity, where we see mass times the Earth's gravitation, and both of these will be interacting with the spring in a way that we will see in this experiment. In terms of period and oscillation, period is t equals 2 pi times the square root of m over k, and we will use this to see how the graphs interact and how a phase shift occurs, similar to Lab 4. A real quick note about human error is how the tracker system works, where each point is plotted by the data collector himself, which would be me. And you see that there is a variation in where these points are, which leads to an unideal system. However, the graphs are very close to what they would be in the real world. Now to break down our data, where we see three graphs to our left. In order, they go time versus x position, time versus y position, and x versus y position. We have to first observe that this first graph, the time versus x position, dampens at a higher rate than the second. And this dampening is seen in the lower amplitude as the graph continues. It diminishes much faster, however, the period of these two remain the same. Now, as I mentioned, there is a phase shift where we see here the middle of the first aligns with the crest of the second, and thus the crest of the first aligns with the middle of the second, or otherwise known as the inflection point. And a quick note about springs is that this shows that the period is the same because there is no change in the force applied in a restorative force based off direction. The only difference is that there is no force acting in the x direction, which is why it diminishes much quicker. Now, finally, in the x versus y graph, we see that the spring travels a further distance in the y direction overall, which we will break down soon. Now, a bit of a what if to understand this data. We will ask, what if there was a constant force other than gravity in the x direction? Now, we see on this previous x versus y graph that the system breaks down to it finally ends in a line on the y-axis where there is no change in the x direction. Now, if there was another constant force acting on this, we would see that the restorative force of the spring would be very similar to the force acting against gravity, leading to a more circular spiral graph than this Lissajous curve, which we see here. Now, in terms of the period of oscillation, if they were unequal, we would see that this would not be a real world system, and that this is something that is impossible to achieve with one constant spring with a stiffness that is predetermined. Now, as a last remark about pendulum and springs, don't forget that these restorative forces are directly proportional to the distortion from another force on the mass. This is a bit wordy, but it just means that there will never be a force from a spring that is greater than the force being enacted in the other direction. And this is why we see the data diminishing and not growing. Thank you guys so much and have a great spring break.